Hello and welcome to the third lecture of the ETCE course. Today we're going to be talking about something called life cycle assessment. This is a very important aspect of sustainability. It pertains to knowing how sustainable or unsustainable, let's say, new technologies are in comparison to other technologies. And in order to make comparisons between different things that aim to do the same thing, you need some more sophisticated tools such as LCAs to make decisions. Last week, Benjamin gave a motivational example where if you want to choose between a battery electric vehicle or an ICE vehicle for, let's say, your next car, there's a lot of things that go into this decision. And we talked about the so-called break-even point in kilometers, after which an EV would have caused fewer emissions than an internal combustion engine vehicle. And basically, the whole point of contention is that even though an EV during manufacturing requires a lot more input resources, material extraction, like heavy metals and rare earth metals, during the actual operation of it, even though you're not using 100% renewable energy, you're still, over the course of its lifetime, in terms of number of kilometers driven, you're having less emissions than a new internal combustion engine vehicle. And when it comes to the actual number of kilometers after which it becomes more sustainable to buy a new EV, it really depended. In this particular example, we compared the couple of engines. In particular, the internal combustion engine was the Volvo's XC480 engine, and compared to like Polestar's new battery electric vehicle, and compared with also different types of mix of electricity that is being put into the battery electric vehicle. So as you can see, and as you might remember, it really depends on the type of energy you're providing to your EV. And depending on this, the break-even point is either very early, let's say around 50,000 kilometers if you're using purely wind energy, and let's say something like what's the global electricity mix? So about 112,000 kilometers. And the European is around about 78,000 kilometers. So if you're in Europe and you decide to buy an EV, after about 78,000 kilometers, you would have caused fewer emissions than an internal combustion engine vehicle. But in this example, they only compared, well, because Polestar wants to sell you this really nice EV, they decided to compare it with only one particular internal combustion engine vehicle. So in terms of scope of the study, it's kind of small. It's one company with comparing one battery electric vehicle with one internal combustion engine vehicle. And that is a very small scope. If you only think whether I should buy a Polestar versus this other Volvo, okay, this is enough. But if you're in general wanting to decide, do I need to buy a battery electric vehicle given where I live in the world or my city, given the electricity charging points in my city, what's the correct choice that I should make? It's a bit more complicated, and this is why we're going to go into life cycle assessment, which is a methodology that we're going to be using to come to a little closer to the answer for this problem. So a little bookish definition of what exactly LCA is. LCA addresses the environmental aspects and potential environmental impacts, for example, the resources and environmental consequences of releases of resources throughout the product's life cycle, from raw material acquisition, so for example, getting rare earth metals for preparing the battery for an EV, or let's say also getting oil from the ocean to fuel your internal combustion engine. Through production, I guess every car manufacturer has to do a lot of production processes in these big factories, so it also takes into account the environmental impact of the processes that goes into the production. And then it comes to the use, where we already know that EVs tend to have a lower impact because they are using the electricity mostly from renewable sources, and also end-of-life treatment. So whether it's recycling or final disposal, so depending on what you do to your vehicle after its life is completed, whether you're recycling the batteries, whether you are, let's say you had an accident and now the car is not viable anymore to be a transportation method. Maybe you can recycle the metals and other parts of the vehicle that you could recycle or reuse, or maybe you just dispose them in some way. So all of the impacts, all of the environmental aspects that go into this is LCA is a methodology that allows you to compress all of this and then compare different methods or different types of products with the same base assumptions. When it comes to, there's many different ways to do an LCA. And turns out there are methodologies that are created by the International Standards Organization. And these methodologies are in these very two framework methods. In particular, these are 14,040 and 14,044. These are two really, really long documents that we don't encourage you to read the whole thing, but you could give it a look. But basically, the first one defines the principles and the framework of the standard, and the second one provides the requirements and the guidelines of how to do an LCA for people who are actually going to go into the field and collect data and look at environmental impacts and so on and so forth. But these are not complete documents. So people who are actually going and doing LCAs of different products actually have to do additional methodologies because it doesn't account for every single scenario that occurs when you're trying to do an LCA. And you kind of have to adapt this for your particular need. One of the example LCA reports that we are going to be keeping an eye on during this lecture and also next week's lecture is the so-called 2020 EU Commission report, where the goal was to determine the environmental impacts of conventional and alternatively fueled vehicles through LCA. So this is kind of the bigger scope study compared to the earlier Polestar study. And instead of Polestar, this is actually prepared by this company called Ricardo Energy and Environment. And it generally follows the standards that I mentioned before. And in terms of scope, you can see in this diagram that not only do they look at electric vehicles and non-electric vehicles, they also look at different types of powertrains. So powertrains are, for example, diesel vehicles, gasoline vehicles, let's say giant trucks, smaller vehicles, so also different types of vehicles. They have a giant scope, so 65 different types of powertrain vehicle combinations, different types of use for the vehicle. Let's say you're trying to use a vehicle for primarily transporting people versus goods, let's say for big LKWs or big trucks. And also different types of food. So from what I recall, they also do, in terms of electricity, different types of renewable sources of electricity, but also different types of fuels. So the state-of-the-art or the baseline of petrol fuels, but also other biofuels and so on and so forth, and different mixtures of many of them. So it's, in general, a much broader study than other studies that happened before. As you can see, there are different studies compared to the EU study. And if you would actually compare this to the Polestar study, you would see like it would probably be one vehicle here, two types of powertrain. So the Polestar study is kind of this really tiny compared to this giant EU study in terms of scope. In general, a life cycle assessment, going forward into what it actually is, has 4 giant stages. And these are not sequential stages, and we will go into what exactly and in what order you do these things in later slides and also in next week's lecture. But in general, the first thing you do is define your goal and the scope, and we will go into this in this week's lecture. And also we do something called LCI, which is the inventory analysis. We will be going into detail with these first 2 things, which is goal and scope definition and inventory analysis in this week's lecture. And next week we will be going more into impact assessment, which is the actual environmental impact that you're going to measure based on the first 2 stages, and also final interpretation, which basically depends that you've done everything else before. Yeah, so let's start. without further ado with goal and scope definition. So all the definitions that we do in this lecture, like today's lecture and next week's lecture, are going to be based on the definitions given by the 14040 standards that we mentioned before. And based on this, the goal of an LCA needs to state what the intended application is of your LCA study, what are the reasons why you're trying to carry the study, and who are the intended audience of the study. So it's kind of important. So if you are making a study for, let's say, just the people in our lecture course, then you have to take into account what is the background of the people who are supposed to be reading this giant document. And you're not going to go into giant, if you are not having an audience who is an expert in the details of combustion technology and everything like this, you cannot really create an LCA with all of these details because your audience cannot analyze or even understand the study. And then it's also very important, if you are intending to compare the results of your study and make your comparative assertions public, it's very important to say that you are intending to do this. Because if you intend to do this, you should make sure you say that in your goal, because this dictates how the rest of your study is going to be carried out. Because if you say, okay, I'm going to compare a battery electric vehicle with an internal combustion engine vehicle, then if this is your goal, you really need to take into account anything that might make a difference in terms of the whole environmental impact from cradle to grave. You cannot, it really determines how good your study is and how much your scope needs to be. For an example, the EU study that we just talked about had the intended application of being a representative selection of road vehicle combinations. So like we said, they had, I think, 65 different combinations of vehicle type and powertrain type and also different fuels. So they were as broad as possible because it's supposed to be intended to enhance the EU Commission's understanding of environmental impact. So the intended audience was the European Commission and the decision makers. This isn't something that a normal person like us can go into and just read. It's really meant to people who are your elected representatives in the EU to basically make decisions on, okay, what should be the year after which we don't allow people to manufacture internal combustion engine vehicles anymore, and what's the year where we cap emission standards, or so on and so forth. So let's talk about the scope. So that was just the goal. The scope is something that I described earlier that pertains to how big your LCA is going to be. And it basically describes some very important things. The most important, in my opinion, are these first two things here, which are the functional units of your systems and the reference flows. And then you talk about your system boundary, which is how big or what are the different things in the life cycle of your different products that you're considering for your LCA. And then you, of course, you go into LCIA, which is the life cycle impact assessment methodology and the types of impacts you're going to analyze. So for an EV, you might consider, okay, if your power is coming from green sources, you consider the environmental impact of getting like electrical energy from wind turbines. Maybe you have to cut a lot of trees, or solar farms also might have to cut a lot of forest area to clear land. And then compare it to how much land or how much environmental impact you're having from, I don't know, digging giant oil wells in the middle of the ocean. So different impacts, not just in terms of CO2 emissions, but also water use, and we will go into more details about LCIA in the future. And also we look at some other things like imitations and data quality requirements, which are, we're not going into too much detail about these two things because these are really specific on your application, but we will look at some examples during this course. So a little more information with functional units. So I'm going to put a lot of emphasis on the first two, which is very important, the functional units and reference flows, because these are the most important definitions that you need before you do any kind of LCA. So I remember Benjamin last week had an example in the performance economy where you have a drill, and essentially the quantifiable output of your drill was, okay, the purpose of a drill is to drill holes. So if you want to do like a LCA of, let's say, a drill, then you need to basically figure out what your functional unit is. And the functional unit is basically a quantified performance of your product system. And in the case of a drill, it could be like 1 million holes drilled. So you basically will define the impacts in relation with this functional unit, which is 1 million holes drilled. So for example, you can say the greenhouse emissions of this drill given 1 million holes drilled is X gigatons of carbon dioxide in the atmosphere. That's an example of an impact you could measure, but its impact is always mapped onto the functional unit that you have. Very related topic, the reference flows. So the measure of the outputs of a process of a given product system, which are required to deliver the performance defined by a functional unit. So the performance defined by your functional unit is, let's say, for example, 1 million holes drilled. That's the performance of your drill that you're trying to measure. And the reference flow is basically what are the outputs of all the processes of your system that are required to satisfy the criteria of 1 million holes drilled. So essentially, you have your goal that you're defining, which is you want 1 million holes drilled, and you compute your reference flow, which is how much of product parts are required to deliver the performance of 1 million holes drilled. We're looking at another example to make it something that you can kind of tangibly look at if you're at home. So let's say you have a dishwasher. Then in that case, you are, let's say, every day or every 2 days, every 3 days, putting dishes in a wash cycle. Hopefully you're doing this once your dishwasher is full and not with a couple dishes inside. Compared to, let's say, you don't have a dishwasher and you're using basically hand wash. Let's say, this is not my kitchen. This is a picture I got from Wikipedia. So I'm sure not all of your kitchens look as horrible as this one, where there's basically 100 different dishes just piling up. Even though it's technically more efficient to do more at once. If you really want to know, is it better to use a hand wash approach versus a dishwasher? If you think about a dishwasher, first you need to manufacture one. You need to maintain it continuously. They use power. Generally, they have to heat up to 60 degrees or something like this to, clean your things. They run for 2 hours compared to just washing them by hand, and where you have a lot more control over how much water you're using. So how do you know which one is better? So we're going to look into some very basic examples in today's lecture, and we will continue this analogy in next week's lecture. And the exercise will be not based on this particular dishwasher example, but based on washing machines. So we are trying to keep the same kind of analogy here, something that you can tangibly imagine in your head, to think about which is better. But the keyword here, better, is the thing that you really need to keep in mind, because you need to understand what do you mean by better. Do you mean in terms of water use? If this is the case, if you look up on Google Scholar water use for dishwashers and versus hand wash, you will see a lot of research papers, I think primarily from funded by companies that produce washing or dishwashers, that say dishwashers actually use a lot less electricity or energy and also water usage, so on and so forth, compared to different types of hand wash techniques. And to a certain extent, this is really true. But when it comes to what is better for you, might be a different case. Like if you're not able to have a dishwasher in the first place, an LCA approach can at least tell you what type of hand wash technique is better for you at home. So when it comes to the scope of an LCA study, and we talked about the functional units and the reference flows, you would have to think about what the functional unit of this whole system is. Remember, now we're trying to really compare two systems, using a dishwasher versus using hand wash to clean your dishes. And the quantified performance of your system is going to be something like, okay, in the example of a drill, it was 1 million holes drilled. So you could say that the performance of your system could be, let's say, 2 million dishes, cups, and cutlery washed. So you can think that 2 million is a huge number. In this case, I just randomly chose that number. You can choose this number as broad, as small as you like. You will understand the reason or reasons why you want to choose a particular number towards the end of this lecture. But essentially, it's just a number of dishes, cups, and cutlery you can wash. You can wash 2 million dishes with a dishwasher, wash 2 million dishes by hand. Of course, that's very difficult. And then compare between the two and see, okay, how much water did I use in this method, how much water I used in this method, and then basically compare which one is better for me. So reference flows, like I said, you can see water usage in terms of if you're getting it from a tap or if you're just getting it from a well. Heating, so if you are living in Germany and your water is heated from the tap from, let's say, a gas heater, then instead of the dishwasher, which generally heats up with an electrical component, you're actually heating with a completely different gas component, which in the winter, maybe it doesn't increase your energy usage in terms of gas that much, but in the summer, maybe it's, I don't know. It really depends on where you live and the type of system you have at home. Also soap, how much soap you're using and how efficient your dishwasher is or how efficient you personally are with washing your dishes. The energy efficiency of your dishwasher and also which washing cycle mode you're using. There's definitely like 5 or 6 different modes for your dishwasher. And depending on this, you can heavily change how much energy you're going to use. And also in terms of this, like something that a hand wash thing doesn't need, of course, you can say a hand wash thing, you need to manufacture the whole, what do you call it, the sink, in which you're going to wash your utensils. In terms of dishwasher, it's a lot bigger. You have to look into the manufacture and the maintenance of dishwasher, which is a lot more. For example, if you look at the EVs example, your battery electric vehicle takes a lot more to produce in terms of manufacturing compared to an internal combustion engine vehicle, but over time, it's kind of using less. So is it the same with a dishwasher? We will see in the course of this lecture. So let's go back in terms of functional units and reference flows, but this time a different example with the EVs and electric and ECEs. In terms of the EU study, basically what they did is they defined many different functional units and reference flows. It's a huge study, so it makes sense that they have a lot of different functional units and reference flows for different types of vehicle combinations. For example, if you're a passenger car, performance of a passenger car depends on what its performance is supposed to be, which is to carry people around. And for carrying people around for a certain number of kilometers. So that is why they decided, okay, the functional unit for a passenger car is going to be some amount of vehicle kilometers. So if they manufacture 2 cars, and 2 cars can do individually 200,000 kilometers in their whole lifespan, the total flow of this system would be 400,000 because there's 2 vehicles. Similarly, a lorry or these giant vehicles, the only purpose of these vehicles is to take, let's say, your Amazon packages to your home. So these are ton kilometers because they're generally carrying a lot of giant packages. Oil maybe, like let's say your big trucks that carry timber over different cities. So their usage is primarily to transport stuff and not people, which is why they are changing the reference flow into tons kilometers and not person or vehicle kilometers. But again, when it comes to urban buses or let's say coach vehicles, they are doing vehicle kilometers again. And then you can really compare only passenger cars, vans, urban buses, and coaches together with each other and say which one has a lower environmental impact for vehicle kilometers. But you cannot compare them with lorries because the reference flows are different completely. Their purpose is completely different, so you don't compare them with each other. Rather, product systems which have the same reference flow can be compared with each other, given that they have the same scope and goal in the study. Another example, so we're looking at, I think, 3-4 examples because it's really important to understand the difference and how to come up with your functional units and reference flows. A few years ago, we did a project in the ETCE Lab where we grow a lot of mushrooms. And we wanted to know if we can use AI systems to make it more efficient and detect okay, is our mushrooms ready to harvest? What state of harvest are they? And also using sensors to detect humidity levels and automatic control of the growth environment. And this is a couple examples here where you see two different types of substrate containers. So on the top you see a substrate container, which is a big plastic box, and you see mushrooms growing out of this hole. And on the bottom you see a big plastic bag, and you see these lot of fruiting bodies coming out of it. The substrate, what I talked about, is basically the medium, which is usually wheat, or basically something that the fungi can actually eat so that it can produce the mushrooms. And basically what we do is we inoculate a sample of fungi inside of the substrate medium. We make sure that it's airtight. Well, we keep a little bit of a ventilation hose for a little bit of incubation for oxygen. And then after your fungi has completely colonized the substrate medium, we open them. So in terms of the first example, the substrate boxes, we basically just expose the hole that we drilled before. The plastic bags, we basically just cut a giant hole, and then the mushrooms come out of them. This might seem like a very, very weird detour, but we will come to like what the functional unit and stuff like this in a couple slides. And after a certain fruiting cycle, so you grow the mushrooms through, you harvest, some more mushrooms grow through these holes, you then destroy, or you basically can discard your substrate medium, the wheat that this thing is growing out of. You can compost them or discard them. And depending on whether you use a plastic box or a bucket or you use a plastic bag, you either throw away the plastic bag. So the plastic bag, because you cannot unbreak a plastic bag, you basically have to throw it away. It's not useful anymore. And yeah, basically you are throwing away a plastic bag that you used for, let's say, a few weeks at the most. And yeah, you're basically contributing to a lot of plastic pollution. Or maybe you have to spend a lot of energy to recycle now this plastic. Yeah, they cannot be reused. They are single use. Comparing this with these substrate pods that we call, which are basically these plastic polypropylene buckets, we seal them by the lid, just like any bucket. And it's very easy to seal and unseal. And these holes that I mentioned before are permanent, like you see this hole here. We take a giant drill bit and we drill holes on four sides, and we stick duct tape when we want to seal them. And we don't have to cut anything when we want to expose them to oxygen and humidity. Basically what this means is once we compost the internal substrate, we can just wash it, use it again. So we don't have to throw it away. And the comparison here is obviously a box or a bucket requires a lot more plastic ahead of time to manufacture it. But it lasts like theoretically infinite cycles, depending on how well you're taking care of it, compared to a plastic bag, which I guess after one cycle you're throwing it away. So we actually wanted to see how many cycles does it take for us to be better than the plastic bag, because substrate bucket, higher cost initially, but over time theoretically should be better than a plastic bag. So we tried to use the life cycle assessment methodology to come up with how much of the environmental impact is different for these two different cases. We didn't do a full LCA study. We did like basic calculations because we did not have a lot of information, which I will go through in a few slides. And the way we defined this is, well, we remember the functional unit, what it's supposed to be. And to define the functional unit, we look at what the purpose of your substrate containers is. And the purpose of them is to contain your substrate medium. So we defined our functional unit as a 3-liter colonizable volume of substrate. And as it turns out, we basically used 3-liter bags and I think also 3-liter buckets. So it was very easy for us to compare the two. And when it comes to the reference flow, buckets require also plastic, same as the plastic bags. So we just amount of plastic or polypropylene required to manufacture, which is exactly equal to the weight of the actual container you're trying to use. And yes, that's basically how you can just define the functional unit and the reference flow. The functional unit is your purpose, what you're trying to use it for. What you really want is volume as much as possible, given input of, let's say, grams of plastic. Obviously, the manufacturing process and everything, because we are not manufacturing them ourselves, are not included inside of the functional units and reference flows, so you cannot really see how much goes into the manufacture of them. But we can do some certain tricks, as I will show you later. Yes, after we go into, I don't know, 4 examples of functional units of reference flows, I hope this is understandable, but obviously you can ask questions after this lecture is over. Let's define what we mean by the system boundary, because this determines all the processes which you're going to include into the study. So given your goal that, let's say you want to compare one product system with the other, that can dictate how big of a boundary do you need in your LCA and what different processes you need to include. So in terms of the EU study, they looked at a lot of things. So vehicle production, so all of the environmental impact for producing the energy and all of the primary energy sources from the point of distribution. So all of the energy required during production, but also, energy required during the production of the vehicle up to the point of distribution. Let's say you're buying it at, let's say, a shop. So even like the electrical usage of the dealership you go to where you buy your car is also included into the study. Production also, so all of the raw materials, processing, component manufacture, logistics, assembly, painting, everything is also included into the production process. Of course, the use of the operation, which is probably where you see the most benefit in an EV. So all the environmental impacts in terms of driving and also impact from maintenance and servicing. You might know that EVs these days are harder sometimes to do maintenance, so I don't know personally because I haven't read the whole study, but maybe they took this into account into the study. Maybe you should take a look and see if you can find that out for yourself. And then at the end, they have the end of life. They also considered how you get rid of this vehicle once it's, let's say, completely out of use, cannot be used anymore. What are the different recycling materials that you can get out of it? What is the energy recovery you can do? Sometimes you burn stuff in order to then get energy out of it. And then what kind of disposal techniques you're using, and are you landfilling some materials? Are you throwing them away into the ocean? Who knows? Yeah, so essentially the boundary of the study is going to be all of these 4 different things. Which is kind of important because if you want to compare different types of like this huge different types of vehicles across manufacturers, across different EU countries, across different types of fuels, across different types of vehicles, you have to be basically using everything. So this includes production of the fuel, production of the actual vehicle, the use of the vehicle, and what happens after the vehicle is thrown away. So very broad study compared to other studies like the Polestar study. Okay, clicker doesn't work. Okay, so in terms of the reusable mushroom pods that we delivered for our Mashar project, because we did not really know the manufacturing process of the buckets or the bags that we are buying, we used theoretical manufacturing processes that we got from an LCA database. If you're interested, we can discuss exactly what we used for this. And also theoretical end-of-life recycling processes. So we basically used benchmarks from databases that say how much in general different manufacturing processes affect the production of different types of plastic and how does that differ from a bucket versus a bag, and then took this into account for our different bags and buckets. So when it comes to a dishwasher and hand wash, you kind of also have to use similar things. So this is completely theoretical because I have not done any LCA on these things. Actually, last year or the years before, we used to make this an exercise for students to do themselves. But this year we're doing washing machines, so we're changing it up a bit. So you really want to take into some things which are common for whether you're doing a dishwasher or you're washing dishes by hand. You want to see, of course, how much water you're using. That must be something you want to take into consideration. So all of the input elementary resources such as water usage, probably also electricity, but this is more something for a dishwasher, so it's not a common thing. Maybe also you take into account the type of distribution system that you use. So depending on where you live, maybe the water distribution system requires, I don't know, maybe you're in a rural village where a water tank that runs on diesel has to come to your locality and pump up to a giant tank that's at the top of your building, and then you have water for the rest of the week. Or maybe you live in a urban city where there is a common system where everyone is getting these complicated pipes from the general civic water system. And then also the treatment system. So you're basically producing a lot of dirty water at the end of your dishwashing, and depending on how you treat your refuse, it really depends on how much your environmental impact you're using. So this can be the type of soap you're using, but let's just keep it simple and just say you're using the same soap for everything. But these are all things that you want to consider inside of your system boundary. And particularly for dishwasher, what is really important to compare, you need to take into account the raw materials. So I guess a lot of steel, maybe different plastics, some electronics. The manufacturing process probably requires giant machines to do this in a production line, so you take this into account as well. Electricity consumption, not just for the production of these machines, but also during use. So they have to heat a lot of water. They also have to spray a lot of water for, I don't know, my personal machine runs for 90 minutes, so I guess that's a lot of energy going into that. And also maintenance and disposal of your dishwasher. So I personally have had one dishwasher that broke and completely shit a bunch of dirty water into my kitchen once, and it was unrepairable, so I basically had to call Sperrmüll and dispose of it. I don't know what happens after you dispose of a washing machine in Germany. I'm sure they do something, but you have to take into account that it takes resources to even take care of the disposal and whether or not you can recycle any of the components after the life of your device is used. And okay, you also need to keep in mind, are you only comparing one dishwasher versus one person washing their hands, or are you going to compare multiple models of manufacturers? This is something that is basically up in the air depending on what you're capable of. If you are not capable of comparing 100 different dishwashers, then it's fine. A lot of the papers that I've seen on, let's say, Google Scholar are like one manufacturer comparing one of their dishwashers to like some people doing some washing. So I haven't personally seen a study that does, let's say, all of the dishwashers that are produced, let's say, a few years compared to, let's say, 2,000 people washing their hands or washing their dishes. So if anyone knows of a study like this, I would be very interested to see, but so far I haven't seen a study this broad like the EU study for EVs. So for hand wash, theoretically there's like at least 3 different types of techniques I can think of for washing your dishes. Of course, you can let your dishes pile up for a lot of time, for over a week, and then wash them all together. Of course, this is really stinky, and you're not considering the health impacts of moldy food in your kitchen. Also, there's multiple techniques like having 2 sinks and filling one sink with soapy water and one sink with just plain water, and then plugging them, and then you're using the soap in one of them, and then you rinse your dishes in the second one, and you don't drain the water towards the end. And this is a method which uses the least amount of water in terms of the domestic side, but also you're not draining away the water after every single dish. Compared to, let's say, if you only have one sink, you you really have to at some point drain the water, get new water, because you can't really rinse everything while there's dirty water in your sink. Also, different people might have different methods of doing this and may take different time. Some people like to have the water pressure slightly higher. Some people cannot bear like really high temperatures of water, so they have to wash it a bit harder. Some people don't like to use gloves, so it's really, you have to do multiple experiments on a really broad section of people in order to get like a comparative result with a dishwasher, which theoretically, given the correct same input, always gives you the same output, whereas you really have to account for other variables when it comes to hand washing. So in general, all processes and flows that are attributable to your analyzed system are supposed to be included, but not all of them are quantitatively relevant. The word quantitatively is kind of important. So let's say the production of the actual sink when it comes to washing the dishes by hand is not that relevant, because the purpose of a dish is not just there for washing your dishes, it also exists for just washing vegetables. Maybe you brush your teeth there because your one at the bathroom is not that good. So you're using the sink for not just washing your dishes. So it has multiple purposes. So when it comes to the whole environmental impact, the amount of impact producing this one sink is probably like that. So it's not that relevant in terms of the bigger picture. So for something like this, when it's less relevant, you can just take estimates. So you don't have to go to the manufacturer of this particular sink and say, hey, what type of method do you use to extrude this steel, and where do you get the steel from? You could just get general estimates from, I don't know, ask ChatGPT, or better, go get a research paper that says, okay, this is the environmental impact of producing steel, and so on and so forth. And this limits your effort. But at some point, you have to say, okay, I cannot really get any information about some things, and this is completely irrelevant, so I'm cutting it off. And basically, this is how you define your system boundary. When something is not that relevant in terms of, even though you got data, it's not affecting the impact of your, or the final assessment of your LCA, you can cut them off, and then they go out of your boundary. But in general, the rule of thumb is your goal and your scope defines what your boundary should be, but you can be a little bit more tricky with the boundary given without changing your goal if you have an estimate of how relevant these certain parts of your system are. So you can cut them off, or you can give estimates or lower quality estimates if it takes too much amount of energy to get the data for everything. We have some more information about the cutoff criteria, and we leave this as a self-study, or you can also look into more details inside of the ICLD handbook. Yes, so now that we're done with the goal, the functional units, the reference flows, and the boundary of your system, kind of the first three things you do when you define an LCA. Also the types of impacts you want to know. So the LCIA methodology is different methods that you use to determine what the environmental impact of a product system is. We will go into a lot of detail into LCIA in next week's lecture. But just to keep it here, for example, in the EU study, they looked at climate change, which is basically CO2 emissions, energy consumption, and so many different things. And for us, basically, in terms of the dishwasher example, you might want to see something like water usage, because you might be using a lot of water, for example. You could be looking at energy consumption of the dishwasher compared to whatever heating you're doing for your water at your domestic home. And then if you have the data, then you consider everything that goes into the manufacturing, and then basically everything here is fair game, basically, and probably even more things that are not mentioned here. Also, for example, ecotoxicity. If the water that's coming out of your drain that after you wash your dishes is being fed into a lake without treatment, that is a lot worse than than not doing that or going through a proper treatment plant. And depending on where you live, the treatment plants are a bit different, and the impacts of the various treatment methods they use are also different. So it really depends on these systems on whether or not, or the type of environmental impact you have at the end of the day. So you really cannot say the question which one is better really cannot be answered with how before you define in your LCA what are the different categories of impacts you're trying to look at. So if you want to look at climate change only, then you say, okay, product X is better than product Y because in terms of climate change, it has lower emissions of CO2. So you can say it's better in terms of climate change, but maybe product B is better in terms of water usage. So you really can't say a binary yes or no, one thing is better than the other, because generally there's different categories in which one thing has a better, more impact than the other. And depending on which impacts you consider are more impactful, or which impacts are more important for you to make a decision between two products, you want to include different categories. And this also defines the type of data you need when it comes to doing the LCA. Limitations and data quality requirements. Like I said, it's an important part which defines if you really are not capable of getting some information, then you have to mention this in your LCA report because you are assuming that it has no impact, or maybe you're assuming a certain impact but you don't have quantitative evidence to support this. For example, in the mushroom R example, we didn't have calculations on the performance of substrate containers. We don't know whether you're producing more mushrooms per substrate container for the bags or the buckets in comparison with each other. We don't know if you get more mushrooms from one compared to the other, which is why we define the functional units in terms of colonizable substrate volume and not amount of mushrooms harvested in grams. So if we had defined, let's say, the functional unit in terms of both colonizable volume, but also grams of amazing tasty mushrooms, maybe also the quality or taste of mushrooms, we would have had or forced to have include this data. And basically that's one limitation of our LCA calculation, which is why we mentioned this at the end. And also contamination rate. We don't know if it is more likely or less likely to have contamination in terms of bad fungi inside of these containers, which is why we mentioned this. So if you're not comparing certain data into your LCA, you mention that you're not doing them, and you change your goal and scope appropriately. Limitations when it comes to dishwashers versus hand wash. If you don't have any information from manufacturers, like maybe manufacturers don't want to tell you because they are afraid of you judging them harshly, they won't give you data on how they are manufacturing them. Maybe you will get better data where how your city is recycling dishwashers that you give away through Sperrmüll. That's probably easier for you to get, but maybe you have to get data estimates that you have to be happy with at the end of the day. And at some point, it would be great that everybody in the world washed their dishes and gave you data on how much water they use, but that's not really feasible. So you're limited to thinking, okay, what are the minimum number of people I need? Are different demographics of people relevant, or is this something that we just do generally? So it's limitations in terms of how many people you can hire to wash dishes. And also human effort, like sure, we are counting the electricity usage of the dishwasher while it's doing this whole thing, but we are not considering, how do you compare or how do you calculate, I don't know, calories used by a person while they're washing their dishes? It's really hard to do this. That's a limitation. You have to then take into account, okay, what does this person eat the last few days? So if you want to put this inside of your study, you need to also compare, okay, the amount of energy this person is consuming versus how much energy that's used over the course of their day to wash dishes. So it really increases the effort that goes into your study if you have to add these externalities. Data quality, like I said, Sometimes you might only have to be happy with estimates of manufacturing recycling data, and you define what your minimum quality is. And let's say you have different sources of information. Let's say ChatGPT is giving us sources, giving you information, but doesn't tell you where this information comes from. We say maybe that's not the best quality information. So we say let's get some better quality. Maybe you get some information from the manufacturer. But of course, those are self-reported, so there isn't no EU body going and looking for the emissions. In comparison with a vehicle, generally in Germany, you have an emissions test every 2 years, and this determines what the emissions of your vehicle is. So it's hard. So sometimes if you have to rely just on the manufacturer's figures, maybe you determine that that isn't the best quality for me. So you might have to go for a higher standard. Maybe you have to go to the factories ourselves, and if you get the permission for that, and then look at how things are being manufactured, and then figure out the data for yourself. So you have to determine for yourself what's my minimum quality of data that I'm putting into my system, because you really want to be completely honest on how accurate your results are going to be, because obviously a study with better quality data is going to have a better readability, better interpretability than a study with low quality data. Now, once we're done defining the goal and the scope of your LCA, let's talk about the next big part of today's lecture, which is lifecycle inventory analysis. So this is the phase where you compile and quantify all the inputs and outputs of the whole product throughout the whole life cycle. So anything that is input into your system inside of your system boundary, and anything that is output of your system inside of your system boundary is fair game, and you need to account for every single input and output. So any product, material, or energy flows that enter your unit processes or exit your unit processes are basically things that you need to take account of for your LCI. And we use this term here called unit process. And basically, a unit process is the smallest element that you consider inside of your lifecycle inventory analysis. I think there is an S missing here for me to change later, and I'll try to remember that, for what your input and output data is being quantified for. So we will go into some examples in the next slides, but basically these are 3 big definitions coming from obviously the ISO standard. Input flows, for example, can look like this. So let's say you have a unit process that goes into your manufacturing. Let's say you are creating the base part of your system. It can have certain inputs that gives an intermediate input to another unit process, but also has some output. Let's say it emits certain water that is basically thrown away into the environment. That's an output flow. But if you manufacture something and feed this into a separate process, that's basically an intermediate flow. So that's an example of different unit systems inside of your product system. This can be super complex. So depending on how fine-grained or the type of data you need, you have to define your flows inside of your system. Some examples on what this can look like. So in terms of a dishwasher, so if you think about the possible inputs that you can have, I think there are arrows missing in this figure. I'll try to fix this later. But essentially, the biggest input or the thing that you want to get cleaned, let's say you have dirty dishes, most importantly, let's say this is your whole system that's actually doing the stuff, or let's say this is your dishwasher. It uses some soap, it takes in some clean water, it uses some electricity, and at the end you have some dirty water and you have some clean dishes. And then depending on the type of dishwasher you have, the actual processes that happen inside of your system can be very different. So you could theoretically not look at anything inside and just say dishes in, soap in, water in, electricity in, dirty water out, and clean dishes out, and use your dishwasher as a black box, kind of as a unit process, and say, well, there is no indivisible process that I can use because I don't know how to get the data for it. And this is most likely what system we have right now, because depending on the type of program you use, depending on the manufacturer, depending on the type of dishwasher, sometimes they pump a lot of clean water in, and I think the first cycle they don't use any soap, and they basically rinse everything. So they heat the water, rinse everything, pump the water out, take some more clean water, heat the water again, then this time they rinse with some soap. Maybe they rinse it higher temperature, maybe they do it for a longer time, and then they pump the water out. So depending on your dishwasher, a lot of these things change. And if you are trying to compare one dishwasher to another dishwasher, or let's say one cycle, one program cycle to another program cycle, you might have to take into account everything like this. But if you really don't have information on particularly how long your dishwasher is pumping and the wattage of your pump and everything like this, you probably have to be the manufacturer if you want to know all of these details. If you don't have this information, you kind of have to treat your whole system as a black box, and the whole unit process is going to be the whole dishwasher, dishes in, water in, dishes out, dirty water out, and electricity, and so on and so forth. But in general, when you talk about a product system, you're not only looking into, one thing we forgot just now was your dishwasher has to come from somewhere. So something we actually forgot is the actual dishwasher itself. So your dishwasher is coming from another system, or maybe that system is part of your system. Let's say raw material acquisition for producing your dishwasher, producing the dishwasher, and then the actual use is probably the system that we just showed here, so in this tiny black box. And then after this, we don't know yet what you do with recycling and reuse and waste treatment. We don't know what happens after your water is treated. Depending on where you live, the water is treated differently, and it's pumped away differently. Energy supply also, we don't know what type of energy any particular dishwasher could have, so you might have to go with, let's say, average electricity mix of households in Germany, or if you know specifically you're doing it for your household, you could do my particular energy supplier. And again, transport, obviously, for your dishwasher itself, if it has to be transported to you, then what are the energy requirements for that? So really, you're looking into all the different types of flows. You're looking into other systems that you're not considering as part of your scope. So everything that's part of your scope is defined here. And all of the different processes or unit processes that you have to take data for are going to be fair game. So if you define your system to be just the usage of your system, then you don't have to get the information or all of the data for how much does it take to produce your washing machine, how much it takes to recycle or reuse them. So it depends on what you set your scope for and what data you have available. It also determines what type of unit processes I have to take into account for capturing data. Okay, so unit flows. Yeah, like I said, one thing we really forgot is the dishwasher. So if you want to take into account, if you have data for the average dishwasher and how much it takes to produce, how much metal it requires, how much plastic, and what it takes to recycle it, you need to take that into account. So the whole inventory analysis thing is not just one thing. You basically putting it into account with the goal and scope definition. So once you have your goal and scope definition, you prepare for collecting your data. And what you do for this is, like I said, you determine what your unit processes are. And once you do this, you then collect your data. Obviously, you create these so-called data collection sheets, like you see on the left side here. You say for every unit process, you make this sheet. You say what are the material inputs coming in, what are the units. Let's say for the actual washing process, let's say it takes material water consumption in terms of liters and how much water it takes, and the origin of that water, like where did this water come from, let's say energy, electricity, so on and so forth. You take this into account for these data collection sheets. So for collection validation, you need to, after you collect your data, you basically need to validate whether they confirm or provide evidence of your data quality requirements. So remember, when you defined your minimum data quality, once you collect this data, you need to make sure that the data you collected supports or is satisfying this minimum quality requirement. You have to do this both while you're collecting your data, because you don't want to collect data only at the end about your quality, and then you just have to do it all over again. So you might want to do this while you're collecting your data, so you can change your data collection process and validation process, and then this can involve establishing mass and energy balances. So for example, let's say I forgot in this slide to include dirty water. So when I first created this figure, I did not account for dirty water in this figure. I just put dirty dishes, clean water, and clean dishes. And what mass calculations and what was the word that I used here? Let me say, yeah, mass and energy balances basically make sure that you calculate the amount of mass of things going in, and once you're looking at the outputs of the process, you make sure that the collective mass of things coming out equals the mass of things coming in. This is very similar to, let's say, balancing chemical equations. So I guess high school chemistry, we've all done that, and you might have to do this basic problem of making sure that the amount of molecules you have going in equals the molecules going out. Obviously, don't go into this much detail for LCA, but you're trying to account for this. And energy balances, in this case, it doesn't make that much sense because you're just using the energy to do different things. But if your dishwasher is producing hot water, this hot water contains some amount of energy because the water is hot. And sometimes, depending on where you are throwing away this water, it can affect the wildlife of the system. Like if you're putting hot water into a lake, this can affect the type of ecosystem this lake has. And depending on this, your environmental assessment can change. So if you did not account for energy balances before, maybe you need to take them into account first and see if there is any impact at all. And if there isn't any impact, then you can remove them with your cutoff criteria because they are not quantitatively relevant anymore. And this validation process can basically let you remove some obvious anomalies. Like I said, I did not think about the rest water before, and you can basically get alternative data if you don't have this data before. And now the most important part that you do, so once you get your data, you validate them, the most important thing you do here is relating the data to the unit process. So based on the initial flowchart that we have for the flows between the unit processes and the flows of all the unit processes related to the reference flow, we take a calculation for everything that we put into the system, and then we relate this to our initial functional unit using the reference flow. We will take into some examples, obviously, because this is a very important part of the LCI process. And the most important thing that we need to remember here is basically the measure of the product or product parts that are required to deliver the performance defined by the functional unit are what's important here. So this calculation that you're doing should result in all the input and output data being referenced to the functional unit. So let's say you said 1 million holes drilled was your functional unit. You say I'm using 20 liters or let's say 2,000 liters of water for the whole process for 1 million holes drilled. That's the input system. And from the output, you can say, I don't know, in kilograms of sawdust generated by this drilling process, if you're only drilling wood, is let's say that you compute and you say I have 10,000 kilograms of sawdust produced over 1 million holes drilled for this whole system. So you're trying to take all of your inputs and output systems, getting the data for how much you're actually using and how much you're actually getting output from, and relating them to your original functional unit. We will take into look some examples. So when it comes to your dishwasher example, let's say you have, actually this slide is out of place. I'm doing the computation later. We will come back to the dishwasher example later. First, let's look into the mushroom example. So we did some experimental estimation, and we had a plastic bag which was 5 liters. And this bag weighed 30 grams, and the amount of colonizable volume that we had after we sealed the bag was around 3 liters. So we can't use the whole 5 liters that the bag has available, because we have to fold it multiple times in order to keep it sealed. So we essentially only have 3 liters at the end of the day to use for colonizable volume. And comparing this with the bucket, because we don't really have to do any folding, we just close the lid, we can use all of the 3 liters. But it weighs 90 grams, so essentially it takes 3 times the amount of plastic. So if you look at the initial functional unit and what it was, we can make some computations. And for example, you can say for 1,000 grams of substrate bags, this will contain, let's say, 1,000 times 3 divided by 30, 100 liters of substrate. What you're trying to do here, you know that it takes 30 grams to produce 3 liters of substrate. What I'm trying to answer is, how many grams does it take to produce, let's say, 100 liters of substrate? So given the same amount of input materials, how much substrate volume do I get? So because the substrate bags require less volume or less amount of plastic in the initial process, you actually get 3 times the amount of substrate colonizable volume compared to the buckets. So this is what this shows here. You're relating this to your initial functional unit, which is amount of colonizable volume. So you see your reference flow, which is the amount of polypropylene, and you relate this to your functional unit. Like I said, we come back to the dishwasher example. So let's say you only doing 1 wash cycle, and inside of your experimental 1 wash cycle, you wash 20 dishes, 20 cups, and 20 cutlery items. And let's say this used about 1.17 kilowatt hours of energy, and about 12 liters of clean water, and about 30 grams of soap. So given this, you know what your experimental estimation is. Now what we need to do is we need to relate this with your functional unit and your reference flow. And like we said, if you remember from initial slides, your functional unit was 2 million dishes, cups, and cutlery washed, and we knew that this 2 million is a huge number. So you can think you basically just have to multiply, like before with the mushroom example. In this case, because you have 1 wash cycle done, you basically, you have 20 dishes, 20 cups, and 20 cutlery items. You divide 1 million or 2 million divided by 20, and that basically means you have to do, you have to multiply this by a certain amount, and that basically means that for 2 million dishes, you have to use 1.17 gigawatt hours of energy or electrical energy, 12 million liters of clean water, and 30,000 kilograms of soap. That's a lot of stuff, but obviously we'll come back to this example and we will see why are we looking at these huge numbers here. And maybe we can change this million example, because it's not really easy to quantify or even imagine 1 million liters or 12 million liters of water. So maybe we'll come back to changing this number in the future. Now let's talk about like a experimental estimation of hand wash. I'm not going to go into what type of technique was used, but during last year's or previous year's experimental things, we asked students to compute how much water they're using in terms of washing dishes. And essentially what you do is you wash 2 dishes, you wash 1 dish or you wash 2 dishes, and you see how much water you're using for every individual thing. And you just do the same thing. You just multiply them by the amount that you want. So because your functional unit is 2 million, if you are collecting data for, let's say, only 2 dishes, 2 cups, and 2 articles of cutlery, and you have the amount of energy used for this, you basically multiply this by 1 million. Or 10 million in this case, because you have to do 2 million dishes washed. And in this case, it takes about 10 gigawatt hours of energy to wash these dishes, 20 milliliters of water, and 400,000 kilograms of soap. But the question is, so if you look at just these numbers, compare them from one to the other, we just said it takes a lot of gigawatt hours of energy. That just basically means that dishwashers are just better. Like if you just looked at these numbers one to one, you will see that dishwashers are better, but there's a problem here. If you look at this 1 million number, you might notice a tiny problem here is if you're multiplying these numbers by 1 million, in this sense this is a dishwasher, you're essentially doing 1 million wash cycles, or you're extrapolating from 1 cycle to 1 million wash cycles. And you're assuming that your dishwasher actually is capable of doing 1 million wash cycles. But normally a dishwasher, I looked up like random numbers, and it tends to be around 5,000 to around 7,000, depending on how well you look after your dishwasher and the type of soap you use, the type of maintenance you do. So if you only looked at one dishwasher compared to washing dishes, these numbers would be great. But we didn't really take into account the number of dishwashers that you used. So turns out if you say that a dishwasher only requires only lasts for about 5,000 to 6,000 life cycles or wash cycles, then not only do you need 1.17 gigawatt hours of energy, 12 million liters of water, this much soap, but you also need 200 more dishwashers, because one dishwasher is not enough for doing your functional unit of 1 or 2 million dishes washed. So that's very important, because it's really not that simple. If you don't take into account the manufacturing process of your dishwasher itself, you will come up with a very different number. So this is what you do. If it turns out that you did not include something before, you revise your initial system boundary. So generally, you relate your data to the functional unit, and then you validate your data for every functional unit. You aggregate them, and then you might have to refine your system boundary. You might have to include things or new unit processes that you did not account for before. Like in this example, we did not account for dishwasher lasting more than 5,000 wash cycles. So you have to now account for the manufacturing process of a dishwasher. You have to account for the disposal of a dishwasher as well. And you might have to exclude some things because they are no longer relevant for you. So you might have to analyze the type of data you have, and based on the data you have, you might have to change your boundary after your initial run of lifecycle inventory analysis is done. So it's a continuing theme here. Lifecycle analysis in general is not just a step-by-step process. You generally come back to initial stages again, and over a certain period of time, you increase how accurate your results are. And after a certain amount of time, the amount of energy you're putting into the system, the amount of data you're putting into the system isn't giving you that much of an increase in accuracy. And at some point, you stop doing your increased data or increased revising of the system boundary. But yeah, essentially, you keep changing this until you have this basic minimum data quality requirement that you have. And then that's your lifecycle inventory analysis. So in a giant summary of what we all learned today, we did a giant deep dive into particularly the first 2 important parts or 2 foundational parts of LCAs, which is the goal and scope definitions. We looked at, 4 examples of functional units and reference flows coming from the Polestar example, the EU report, the mushroom project, dishwashers versus hand washing. So I hope at this point you are kind of familiar with how to create a functional unit and reference flow for yourself if you had to do it. And we also talked about inventory analysis and how you can define unit processes and process flows for yourself. And once you do this and you collect the data for your unit processes, how do you relate this data to your functional units in the first place? And yeah, today's exercise, like I said, is going to be part 1 for LCAs. The main goal is going to be to compare the water and power consumption of washing machines. And your main task is going to be defining the goal and scope. And because we did LCI and goal and scope today, this is what we're going to be doing. Goal and scope definition, defining the unit processes, and determining all the unit input and output flows of the system. And this is basically all that we will do interactively. So you don't have to do this all by yourself. We will do some of this interactively during the lecture. And for a homework that you have to do for the next 2 weeks is basically to collect data for yourself, for your personal washing machine. I hope everybody is washing their clothes. So I think everybody is able to do this. You collect LCI data based on the goal and scope definition and the LCI criteria that we defined during the interactive exercise session. And then we assign these to the functional unit. So you have to do this for yourself using the examples that we provided inside of this lecture. And as usual, if you have questions, we will take a 15-minute break. And then we gather back here for more questions, if you have any questions about LCA. And then we go into an interactive exercise session. Thank you for your attention.